Hi, I am Orestes Manzanilla from Polytechnique Montréal, and in the next 15 minutes I am going to share with you one of our most recent research projects, which will appear in the IEEE Access Journal. It consists on a machine learning framework to detect sleeping cells, a difficult-to-detect kind of base station failure in cellular networks. It is based on Internet of Things traffic of a smart city's cellular infrastructure. This work was done along with Filippo Malandra, Hakim Mellah, Constant Ouete, and Brunilde Sansot. Now, a little bit of context. It is well known that cities' populations are increasing every day. Moreover, the quantity of the Internet of Things devices is increasing, in part because each day there is more people using them, but also because there is an explosion in the quantity of systems and applications that use them. The Internet of Things refers to all the interrelated devices that transmit data over a network or the Internet without actively requiring a human action. An example of human-type traffic would be a video call. On the other hand, the data packets being sent by a smart meter to report energy consumption to the electricity company would be considered machine-to-machine traffic and a part of the IoT. As a consequence, the cellular network infrastructure transmits traffic generated both by machines and humans. In some cases, the network will be sliced into separate networks. In others, humans and machines will compete for the resources of the network. There has been a lot of research studying traffic generated by humans. However, as the quantity of traffic generated by machines increases, so will do our need to understand its patterns. In this work, we have simulated the Internet of Things traffic in order to analyze it. In many cases, the IoT applications that help automating our lives in a smart city will use the cellular infrastructure. In some cases, our smart devices connect directly to the Internet. In others, we use services that depend on data transmitted by sensors or actuators. Depending on the requirements of each system, a banal failure in the network may disrupt one of them. As an example, an excessive communication delay for a sensor of the smart grid may impede its protection system from avoiding a blackout. One of the most difficult types of cellular network failures are the so-called sleeping cells, which is the problem we tackle in this project. But what is a sleeping cell exactly? When a cell falls asleep, it works like a yellow light in the traffic lights. If a car is already crossing the intersection, it will not stop, but it will continue its way to the other side. Otherwise, it stops, or it should stop at least, until the light is green again. In the same way, a sleeping cell continues transmitting packets from devices already connected. On the other hand, those sending a request for access are not attended. The big difference between intersections with a yellow traffic light and a sleeping cell is that while we know the traffic lights will change in a couple of seconds, cells remain asleep until the operator fixes the problem. Let us see an example. In this figure, we see each device connected to the antenna that gives the best quality of signal. However, when a cell falls asleep, devices normally served by that cell will send their access requests to nearby ones. It is true that a sleeping cell still does some work, transmitting data that was already in transmission when it fell asleep, but this will eventually end. At that point, the cell is no longer doing anything. We call this state being catatonic. Nearby cells receiving the extra traffic become also more congested progressively, which may degrade their performance. But why does this matter? There are many systems that have different degrees of criticality for the population in a smart city. An example of a very critical one is the power system. As it becomes more and more complex with the use of distributed renewable energy sources, the importance of its vigilance and automation is more critical. A degradation of communications performance may hinder the system's ability to avoid a blackout. There are other systems that automate or adapt the city services to our needs in real time, like intelligent transportation systems, smart parking applications, and waste management systems. Finally, performance degradation may also affect the human traffic, like the quality of our streaming services, our internet browsing, or our video calls. What makes sleeping cell failures more difficult to deal with is the fact that they are very difficult for the operator to detect. Days, and in some cases weeks, may pass before the failure is identified, which is only the first step towards compensation measurements, diagnosis, and finally solving the problem. No alarms in a panel will signal these failures, and because there might be some traffic being transmitted for some days, it may not be obvious that there is a problem. So, what kind of tool would we like to offer an operator to deal with this problem? For an operator, this is how the cells of a smart city would look like, even when there is one cell that has fallen asleep. With the framework we propose, we aim to give the operator a tool that would be like a set of augmented reality glasses loaded with a trained machine learning model. This would be a model that has learned how to detect sleeping cells even when the traffic is exclusively or mostly produced by machines. The glasses would study each cell not only by analyzing its own performance, but also by looking at any possible perturbation it might be causing to the neighbor cells. As a result, when the operator puts on the glasses, he could easily see which cells are awake and which cells are asleep. He can then put in place compensation measures and start the diagnosis of the sleeping cell base station. Our research question was, can we detect this type of failure by looking at the aggregated traces of the traffic of the machines? This question is important because the data generated by the network is huge and it is extremely convenient for operators to work only with aggregated data. So this is a question that arises as part of a bigger goal that our research team has, which is detecting and predicting the quality of experience of a smart city application enabled by the Internet of Things from the point of view of the cellular network performance. Our working framework to tackle this, among other questions, is the use of simulators built to be as realistic as possible by using open data from the city's infrastructure. The approach is to always look forwards in a future where the IoT is expected to be pervasive. In particular, for this project, we used a large-scale LTE simulator based on real telecom infrastructure and real potential locations for the IoT devices in a large city. This simulator has an interactive graphical interface that is publicly available online in the URL that is shown in the screen right now. In it, users can simulate total and partial sleeping cell failures and observe how the performance is affected by them over time. This simulator was built using advanced propagation models to compute the received signal strength in each location of the city. This project was undertaken with focus on three main issues. The first one is that we are looking for patterns that are not easy to see in the data. The second one is that we choose to detect the patterns looking at aggregations of data instead of the original one. It is well known that aggregating data is a process that hides the probability distributions of the original data. For example, averages of values following a uniform distribution will be distributed as a normal, and it will be very hard to guess how the original values were distributed. Finally, we know that sleeping cells affect nearby cells. However, the ones affected may not necessarily be the closest ones, so using distances to determine if a cell is a neighbor or not is a bad idea. Our strategy to tackle these issues consists firstly on using high-order statistics to aggregate data in an effort to keep as much information as possible about the shape of the original distribution of the data. We aggregate by computing not only means and variances, but also asymmetry, percentiles, among others. We chose to look not only at the cell hypothetically sleeping, but also to its neighbors. Finally, as mentioned before, we made a new definition of what a neighbor is. We consider among a cell's neighbors only those with a high enough probability of attending the traffic that should be served by the cell that is sleeping. So I am going to speak now about the benefits that our proposed framework has shown in our experiments. First, it has shown to be simple. Very well-known machine learning classifiers have given excellent results. Second, it is very precise in its detection while also giving a very low false alarm rate. Thirdly, it is quick to give a response. Once trained, it gives results using only data from 5 to 30 minutes of traffic. Finally, it opens possibilities for future research. It shows that the way data is being aggregated is useful, and it is able to preserve the patterns of the original data, which makes it promising to be used in other machine learning and statistical tasks. Now I will explain how does the method work. It starts by capturing the signal strength at each location in the simulator. This allows creating at each device location a priority list of the antennas it receives ordered by their signal strength. Each device is assumed to connect to the first base station of their list, which is the one with the highest received strength. When a base station falls asleep, ceasing to provide access to the network, each of the devices it served will choose the next antenna in their list to send their requests for access. This logic allows us to compute the probability of each cell of receiving the traffic normally attended by the one that fell asleep. This way, instead of building the set of neighbors by considering the closest ones, it will be made of those with a high probability of receiving its traffic and therefore experiencing performance degradation. After we have determined which are the neighboring cells of the one that could, hypothetically speaking, be asleep, we get the performance data along with the one of the cell under study. Both the cell under study and its neighbors' data are aggregated in non-overlapping time bins. The statistics computed in the aggregation process are concatenated into a vector. We call this the feature vector, and we expect it to have enough information for the machine learning model to guess if the cell under study is or not asleep. The machine learning model is fed with these vectors along with one label for each one, indicating whether the cell was asleep or not. We know this as this is a part of the parameters we fed the simulator with when we ran our experiments. The end goal is that all the devices in the smart city connected to the cellular infrastructure are served with a performance that is good enough for the application to achieve its goal. Which means that the application manager will be satisfied with the telco operator. For him, the application represents, hopefully, an increase in his ability to detect, compensate, diagnose, and fix sleeping cell failures before there is a noticeable degradation of the service. This work was supported by Polytechnique Montréal, Ericsson, Natural Sciences and Engineering Research Council of Canada, the Institute for Data Valorization IVADO, Calcul Québec, and Compute Canada. This concludes our video summarizing our paper, A Machine Learning Framework for Sleeping Cell Detection in a Smart City Internet of Things telecommunications infrastructure. You are invited to read the accompanying paper to appear in the IEEE Access journal for more details.